Welcome to this short video tutorial on how to install and use the R scripts provided as supplemental data 3 of the paper published in Journal of Analytical Toxicology. These scripts will allow you to select the adequate model for your calibration curves, including weighting and model order, and to validate the chosen model. The first step is to install R and RStudio on your computer. R is an open source programming language and software for statistical computing. It can be found free of charge at r-project.org. To install it on your computer, you need to click on the CRAN link under the download section of the left-hand side of the website. CRAN, which stands for the Comprehensive R Archive Network, is a list of different servers or mirrors that contain the R software which you can download. Choose one of the mirrors, click on it, and install R on your computer by selecting the appropriate version for you. RStudio can be found at rstudio.com. It is a graphical, user-friendly interface for coding in R. To obtain RStudio, simply click on Products, RStudio, and select the free open source edition of the software. A commercial licensed version of the software exists for those who are interested. Once R and RStudio are installed on your computer, you need to put on your desktop an uncompressed version of the supplemental data 3 file. You therefore need to extract the zip file and send it on your desktop. This is what I did here. This folder contains the 4 scripts which will perform the data analysis. You will now need to set up the R environment. Open RStudio. The first necessary step is to install the statistical computing package called NBTnorm. In the bottom right panel, in the Packages tab, click on Install. Search for the package NBTnorm, select it, and launch installation. Since the package is retrieved on a website, you must have an internet connection for the installation to be successful. Once the step is complete, a line will say that the package NBTnorm was successfully unpacked. Let's now take a look at the only script you will need to work in, RunMe. The 3 other scripts you see here are necessary, but they will run in the background. When you open RunMe, you see in the header here that a number of parameters may be set by the user. The first one is the directory, right here on line 6. The directory tells RStudio where to retrieve the files containing the measurements and where to drop the file containing the results. The easiest way to define the working directory is to place your cursor in the console and then click on Session, Set Working Directory to Source File Location. This sets the working directory as the folder in which this script is actually present. Now, you have set the working directory inside the console, but you also need to set it inside the script. The easiest way to do this is to take the path shown in the console, copy it, and paste it in the script. Then the directory is properly set. The next parameter on line 8 is the file name. This is the file where the raw data, meaning the concentration levels and replicate measurements, will be retrieved. It needs to be a text file where the first column contains the concentrations and the subsequent columns contain the replicate measurements. Probably the easiest way to do this is to have an Excel file ready with a table, like this one here, where again concentrations are in the first column here, and measurements are in the subsequent columns. From a table like this, all that needs to be done is to select the data, only data without headers, copy it, and paste it in a notepad file. This file is to be saved in the working directory here. I will save this file as test.txt. Now I can close this, and in my working directory I can check that indeed I have my file containing my data. So I can now copy this file name into my script in R. So my file name is test.txt. Next, the result file name needs to be specified on line 9. The output of the analysis is programmed to be saved in a text file. The name you wish to give this results file should be indicated here. For this analysis, I will indicate to save the results as results_test.txt. Here we go. The next option on line 10 is called DEC, which is short for decimal. This option is present for the French-speaking part of the world, of which I happen to be a member. For some reason, we use comma as a decimal separator instead of a dot. Most of you will be in the English-speaking countries and use a dot as the DEC parameter here and will never change it. But if ever you use a comma as a decimal separator, here's a place to specify it. Two other parameters indicated here on lines 11 and 12 are number grid and B. They relate to the bootstrapping procedure used in the residuals normality testing, and you will most likely never change them. The next parameter on line 13 is called stat. It defines which normality test will be used for model validation. When stat is set as 1, the Kolmogorov-Smirnov test will be used. When stat is set as 2, the Kramer-von Mises test will be used. I personally favor the Kramer-von Mises test, so I will set the stat as 2. Finally, on line 14, you have the alpha value, which can be changed. It is the level of significance of all the tests performed here. It is a good idea to leave it at 0.05 because it's a generally accepted standard, unless you have a very specific reason to change it. Once all of the different parameters are set, then save the script here and click on Source at the top right of the panel. When a script is running, a small stop sign will appear at the top right of the console panel. This means the program is compiling. Depending on the computer you are on, this might take more or less time, but I have never seen it take more than a minute. Here we go, we have our results. The output of the code, it appears in the console, so you can take a quick look at the results you have obtained. Here the chosen model was quadratic, 1/x². But most of you are working in accredited labs, which entail keeping a certain paper trail during validation procedures. To help with that, the script will save a copy of those results in a text file placed in the working directory folder. So here I have my text file results. If I open it, I see that this is exactly the same thing as the output that was shown in the console. So if we look at the results, first of all, here we have the F-test for heteroscedasticity. The p-value is way below 0.05, which means waiting will be necessary for this calibration model. The results of the variance evaluation for weight selection show the scores of the different weights. The weight with the smallest score will be chosen, here 1/x². Next, we have the partial F-test for model order selection. Since the resulting p-value is way below 0.05, a quadratic model is selected. And then finally, we want to test that the model selected is a valid model, and so we perform normality of the standardized residuals. The test used in this instance was Kramer-von Mises, which is what was selected in the R script. The resulting value is way above 0.05, and so the validation test is passed. At the end here, we have a final summary of the model chosen and the associated calibration equation. Two other files are created by the script PDF files. The first one, calibration curve, contains, well, you guessed it, the calibration curve graph with all the data points plotted with the regression line calculated with the selected model. The other PDF file, variance, contains a variance plot. So this shows a graph of the variance of the replicate measurements versus concentration. Here we observe sort of an inverse parabolic shape, which indicates that 1/x squared was a good choice for the weighting factor. So there you go. This is how you use the scripts in order to choose and validate a calibration model. Now you go and have fun with your data, and if you have questions, don't hesitate to email me.